organizers of online math physics seminar. So the title of my talk is the non-relativistic limit of higher spin fields and planar Schrödinger equation in 3 dimensions. So this work is done partly in DU and partly in BRAC, and under the supervision of Dr. Rakibur Rahman. Okay. So there's the outline. I hope everybody can see my screen. If you have any questions, please feel free to ask me and interrupt me. And I go on. Okay. So this is roughly the outline of the talk. We'll start with some motivation, and we'll talk about difficulty in taking non-relativistic limit for real fields, and we'll talk about 2 approaches to reach planar Schrödinger equation. Basically, one is the equation of motion approach, and another is through Lagrangian density approach. So, acknowledgement. I am very thankful to Dr. Rakibur Rahman for giving me this opportunity to learn and research under his wing. And I'm also thankful to Dr. Momin and Dr. Majumdar and many other countless friends and teachers who have helped me along the way. Motivation to study higher spin fields. So what is the motivation? Why should we study higher spin fields? Higher spin fields appear naturally in string theory. So in high energies, people are looking at modified gravity theories. So they might be interested in that as well. They're also interested in dark matter, and higher spin is also important as a collective excitation in a condensed matter system. So yeah, so it's good to study higher spin fields and their consistency, interactions, and all that. Here we are considering the non-relativistic limit of higher spin fields in 3 dimensions.
Sorry, I have a very nice question. So what are some examples where higher spin arise in condensed matter?
Some collective excitations. Exactly, I haven't researched. So they have this Majorana and Weil. They're not high spin, obviously, but they are collective excitation. They are not fundamental. Obviously, in high energy physics, there are examples. Higher resonances of particle interactions. They have a particle multiplex. They have higher spins, like we have omega minus. So, yeah.
Okay, thank you.
Okay, so what is the difficulty in taking non-relativistic limit of real field? So let's take a Klein-Gordon equation for a real scalar field, and we break down the box, and which is D'Alembertian, and we have this operator. Now, if I naively take it, so this is the equation. Now, if I go ahead and take the non-relativistic limit, which is tantamount to saying speed of light goes to infinity, this dynamical term drops off, and you end up having an equation which is non-dynamical. So basically, a Laplacian. You have 1 over lambda, which is the Compton wavelength. So pretty much a non-dynamical equation, and which is you don't want. You want to understand the dynamics of theory. So therefore, just taking the non-relativistic limit of a real scalar field doesn't work. So what you do is you consider a complex scalar field rather than a real scalar field, and you write the complex scalar field as a phase factor, which has the rest mass energy, which is factor e to the power minus I mc squared t by h bar, and psi, which is another complex field. So it's essentially a projective representation, and you plug this into the Klein-Gordon equation. And after a few simplifications, you end up getting this result. And now if you take the c goes to infinity limit of this equation, you do get Schrödinger equation. So this is the first order entire equation. So, so that's the approach that works for equation of motion. So if you start with equation of motion of a relativistic theory, in this case, relativistic theory of a spin zero particle, which is represented by a complex scalar field, then this is how you get it. You have to take this into account. So, any questions? Okay. So this comes. So there's a deep explanation why this thing works. It's because the Bargmann group, symmetry group of the Schrödinger equation is actually has one more generator than the Lorentz group. That is the central extension, which is the mass term. So naturally, one should consider a projective representation given by the mass, which is the U1 for this term. That's the reason why this one works and this one doesn't work. All right. So
again, I have a naive question. So what do you mean by Bargmann representation of Schrödinger?
No, Bargmann symmetry group.
Yes. So could you please? I mean, I don't know what. Could you please tell me what symmetry group?
If you have, so you have this Lorentz algebra, and then if you take, if you do the contraction, which is the taking the non-relativistic limit of the Lorentz algebra, then you have, so what essentially, so you have this algebra, so Gi, Jj, minus 1i, Jk, Jk, Ji, Kj. So you have these stuffs, right? Ki, Kj, some Kj, with some Ji, and other stuff. Okay, so so importantly, what I need is Ji, Pj, which would be some Pk and stuff. So so this defines Lorentz algebra. Okay. So these generators, if you exponentiate, you get the Lorentz group. So so what you do is you go you try to take the non-relativistic limit that this goes to 0, which I don't want to think this is very large, infinity. So this is the Inunu-Wigner contraction. I'm going to probably not make a mistake writing the name. I'm just going to say some contraction, group contraction. So in this case, algebra contraction. So Inunu-Wigner. Okay. So okay. So one takes this contraction of this Lorentz algebra, and one ends up getting what is known as the Bargmann algebra. Okay. So Bargmann algebra. So the interesting bit is that, so these are, okay, so the momentum has the zeroth component is the Hamiltonian, and the Hamiltonian has, so if you see the non-relativistic behavior, you want to have this decomposition, okay, where M is the rest mass and W is some non-rest mass part. It's purely kinetic. Probably goes like V squared, goes like V squared. Okay. So so you see that because of this decomposition, you pick up a central extension. Okay. So in the Bargmann algebra, you have one more generator. This thing, and this gives rise to a U1 global phase symmetry. Okay. So essentially, one should consider, because of this central extension of the group, one should consider a projective representation instead of a real representation. And therefore, one should consider a complex field. Does it roughly answer your question?
Okay, maybe not everything clear, but maybe just carry on.
Reference is a Weinberg one.
May I add a few lines to what Abhijeet just said, please?
Yeah, sure, sir.
Okay. So the point is that in a relativistic theory, mass is a quadratic thing. We know that, right? But in a non-relativistic theory, is described by the Inonu-Wigner n symmetry generators, whereas in a non-relativistic theory, you take the Newton's law and you want to find its symmetry, you see that there are 11 symmetry generators, and every particle has a constant mass, and this mass turns out to be a central charge. So if different objects have different masses, those masses are different simply because they are different uh, um, objects with different values of the central charge. So mass turns out not to be a Casimir of the theory, but a central charge. So the mass commutes with all the other generators. Okay, so now for a non-relativistic theory, you need a non-relativistic limit of the Poincare group plus mass, which is the Bergman group. Okay.
Okay, yeah, that helps really. Thanks.
So moving forward, here. So yeah, okay, good. So so there's a simple field theoretic model one can consider. So let us consider a Lorentz invariant scalar field theory, which is given by this Lagrangian. Okay, and by Euler-Lagrange equation, one gets this equation of motion, which is the Klein-Gordon equation. Now, to study the non-relativistic limit, let us consider this decomposition, where the energy can be split into mass and some kinetic part, which is, in this case, is very much smaller than mass. So we write this phi in terms of, again, a projective part and then a phase part and the phi, which is, so the condition is that this phi is oscillating pretty slowly compared to this e to the power minus imt term, because of this condition. So you plug this in to this relativistic equation of motion. Okay, and after some algebra, you end up getting this this expression. And from here, you see there is a second derivative term of the slowly oscillating field, and this is much smaller because it's oscillating very slowly, and you're taking the second derivative, which is contributing less than this term. So this is the most dominant term. So you can drop this term in comparison to this term, and therefore this term cancel off the rest term, and you end up getting the Schrödinger equation. So I hope you can see the same idea reverberates actually. So this is the key to everything. It has a good theoretic example, explanation, and also complete calculational proof that it works. So now, so the spin zero field is basically this. So this is how one gets Schrödinger equation, or one takes the non-relativistic limit for higher spin, for spin zero field in 3 dimensions, or in this case, the dimension is not very clear, but it works out. So now I'm going to specifically talk about 3 dimensions. So, okay. So, right. So I'm going to talk about, so my idea, so there are 2 approaches. So one is the equation of motion approach, and another is the Lagrangian density approach. Okay, so first I'm going to talk about number 1, and then I'll talk about number 2. So, so my talk will be, I will consider very simple case of spin 1, and I will show you the algorithm and tell you that how, and show you how to follow it up in higher spins, or what subtleties may come in if you consider spin 3 and spin 5. But spin 3 is one level more subtlety, but everything else follows the same algorithm. Okay, so let me get started with the spin 1 equation of motion approach. Spin 1. Okay, so we start with the equation of motion in 4D. So we start with a massless massless field phi m in 4D. So what is the m here? The m is the vector index, space-time index. So here m stands for, so some conventions I should have mentioned. Let me do it right now. So here my conventions are, I'm going to use light cone coordinates, so which are x plus minus and xi. So what are x plus minus? X plus minus is defined by this. Okay. And my I runs from 1 to 2. And okay. Now we're working in the Minkowski spacetime. So, okay, good. So, okay. So what is the equation of motion for a massless field phi m? It's a vector field, spin 1. This is this. Now we impose light cone gauge condition. That is phi minus is equal to 0. So one can show the light cone gauge condition is actually a complete gauge fixing condition. Therefore, you don't get any residual gauge symmetry. So one does is one plugs this in equation 1, this equation of motion, and you get the constraint that divergence must be 0. Okay. So this goes by the name of transversality constraint or condition for spin 1. Now let us have a quick count of the degrees of freedom. So we had 4 degrees of freedom, phi m. We have 4 dUf. And because of this equation 2, so let me give the name equation 3. Because of the light cone gauge condition, essentially sets one of the components to 0. So -1 for equation 2. And there is the transversality condition, is -1 for equation 3. Therefore, you have 2 degrees of freedom left over. And that's it, because we know from Wigner's analysis of Poincare group that massless fields have massless spin 1 has 2 degrees of freedom in 4 dimensions. So it's true for any spin. I think it's greater than 0 or greater than 0 perhaps. For any spin greater than 0, you have only 2 dUs. That was the theorem. That's the conclusion he reaches. So yeah, so we are consistent with that. So again, for reference, Weinberg. Okay, so next we see that we have so we have some freedom here. You can see that, okay, phi minus is given, but there is some freedom here that which one you choose to be auxiliary. You have 2 dUf, so out of 3 you have to choose 2. Okay, so naturally I chose my I, 1, 2 components to be independent, and plus to be the remaining auxiliary variable. So I write this constraint, equation 3. Okay, I express this as this equation. So just explicitly saying that this is actually an auxiliary variable. This is completely determined by these two guys. So now we combine these two, phi 1 and phi 2, phi1 and phi2, we combine them into a complex field phi. So this is our new field phi, which has the same DOF, but it is a complex field instead of two real fields for reasons we explained earlier. Okay. So therefore, we should be working with complex coordinates. So this is our complex coordinates. So what one can show that with this complex coordinates, one can express this auxiliary equation in terms of this. And so far we haven't done anything except for just using light cone gauge condition. Okay? And still it's a massless theory in 4 dimensions. Now we're going to do a dimensional reduction. Okay. And this is the idea of Birkhoff et al. So okay. So what they came up with is they came up with this ansatz. So essentially what they're doing is that they're taking the minus derivative of the psi a to be psi a. So essentially dimensional reducing a dimension going from 4D to 3D. And one obtains a mass from going from 4D to 3D. So one gets this idea also from Kaluza-Klein reduction as well. So this is their answer.
Sorry, again a naive question. I didn't understand how space-time dimension changed by their ansatz. So you were 4D so far, and then?
Yeah, so this is one of the derivatives, right?
Yes.
Yeah, so now whenever this derivative comes into our theory, okay, we're going to change it to this. So essentially dropping one dimension. We had 4 dimensions, x2. So when you change, so your field doesn't depend on d minus. It just becomes a number.
Okay.
So I can add a few lines here, right? This sort of technique is called dimensional reduction. It's not like Kaluza-Klein. It's not like that where you integrate out one dimension. In this case, you simply assume that your fields are not functions of a particular space dimensions, if you like, right? So that you can drop the dependency and drop all the derivatives, right, with respect to that particular dimension. Then the dynamical problem will be reduced to one dimension.
Okay, so this is like we have to impose this condition, like we assume that the field doesn't depends on some of the coordinate, right? It's like an assumption, an extra condition imposed, right?
I think it follows. I think it follows on shell, right? I think that Abhijeet can say it, right?
Yeah. Yes, sir. It's a null reduction. So yeah.
Sorry.
So
again,
his question was why does null reduction make sense to begin with, right? Why can you assume that the
yes. Why I can assume that?
Yes, fields are not a function of a particular space-time dimension or a linear combination thereof. And I said that you can prove that from the equations of motion. Is that right, Abhijeet?
Well, Yeah, you can use equation of motion to prove it. I think obviously you just okay. So you take this equation, you write down for d minus. So uh, so um, so to break it down, what happens? The box have okay. The box will have like d plus square nabla square, which is di nabla square, and some di square, and it acts on psi, or in this case phi. And you have, yeah, so this is a master stereo, right? So right, so I think the way I would say that because of light cone coordinates, you have this x plus and x minus. Okay, so the fields okay, so fields can propagate on x plus and x minus. Okay, so you can drop, so by saying that phi does not depend on x minus, there is no dependency, like this means that I'm really saying that this is not propagate, I'm not considering this mode.
So just to clarify, are you not considering, or it can be proven that this is not the case? Is it an assumption or it is an proof? Which one?
Well, in this case, no. In this case, I'm not proving it.
So you are assuming this is
I'm
true.
assuming.
So this is an additional condition you are putting on your theory. Am I right?
Yeah, from my end.
Okay.
Second end. So from my end, I'm trying to convince you that this is, well, this is an answer. Actually, I'm trying to convince you that what we are doing is basically saying that we are not considering this.
Okay. Okay. Thank you.
Consistency can be proven, but as we move along. So because we get the right equation at the end of the day, right dynamical equation at the end of the day, and everything, there is no inconsistency if we take this. Okay. Okay. Good. So okay, good. So where were we? So we had, so we used them. So we are going to use these answers now. We have the answers, and what we're going to do is we're going to plug this in to our dynamical equation. So our dynamical equation was this, and this box, actually my box representation needs to be rechecked. I think I wrote something wrong here in the box representation. This is not going to be the box representation. I'm sorry, terribly sorry. I got carried away. So this box representation, what works is d square minus del square, right? Normal coordinates. But if you go to light cone coordinates, this goes like this actually. So essentially, what is saying that you're dropping this dependence. So you're essentially killing off one of the derivatives here. Same thing. Okay, so it becomes a first order in the light cone coordinates. So your box phi m was 0. Okay, let me show you the equation again. So this is dropped because of this condition. So I only have a free, just a wave equation in 4 dimensions. So by using that answer, okay, now I'm going to write. So before that, I'm going to write in the light cone coordinates this thing. So okay, so there is another thing I again missed. Again I got carried away. Please ask me questions when you see there is something wrong with this. This really is d naught square minus d3 square, right? Psi equal to 1, 2. So I dropped this factor as well. I'm sorry, I'm a bit got a bit carried away. Okay. Are you with me, Bhaiya?
Yes, I'm there.
Okay. So yeah, one of the coordinates took it away, and it was so minus becomes del r square phi m. Good. So now this part becomes I m over h bar phi m equal to del I. So okay, I should not have said phi m. I should have said phi. But I think you understand. Because okay. So here, where is that? Yeah. Okay, there is a phi here. So I should have said, okay, this is a capital phi. I should have used. Should have used capital phi here. And I should have used capital phi everywhere. Because after all, I have only 2 degrees of freedom left. Good. So, okay. So now you can easily see what's going to happen is one obtains Schrödinger equation. Okay. So from this line to this line, you can easily see this is going to come out. Is there any question? Any line you want to review? How this derivation came through? Bhaiya, any question?
No, it's good for me. Thank you.
So please ask me any questions. Could be any question. Now I'm a very naive person, as you can see. I'm making a lot of naive mistakes, which is, I think it's all right. We'll learn as long as we're all learning. All right. Okay, so so same. So this is the idea, and this idea can be generalized to a higher spin boson. So I'm considering, as you can see, I considered a bosonic field, an integer spin field. So this idea can be generalized to spin 2, which actually, or spin 3 and all other bosonic fields. So for spin 2, this work was done by Barkshoff originally. So they were considering something else. They wanted to consider the non-relativistic limit of spin 2 to understand um, um, some gaps more in quantum Hall effects. So they were interested in something else, but we took the inspiration from there and we thought, okay, so can we generalize that procedure for arbitrary higher spin fields, not just bosons but for fermions. So in this case, so I'm talking about bosons. So for spin 2, you can see you can start again with the equation of motion. So that's the Frontstall equation for a massless totally symmetric spin 2 field. Okay, so this is important. We're going to describe spin particle by the totally symmetric field. Okay. And H prime is the trace, and you again go to the light cone coordinates. It's in 40. You impose the light cone gauge condition, and then you write it down, you plug it into the equation, and you find this constraint. And from the constraint, you recover that this part, which is the divergence, must be 0, and the trace itself must be 0. So you need this condition to have the right degree of freedom in 4 dimensions and the consistency that comes with it. So using the light cone gauge and above constraints, so these 2 constraints and the light cone gauge condition, I could show the full picture. Okay, so you can write H plus or something, some component. So writing this down, okay, which is defined by this equation, which is essentially divergence. So you write it down and you use these constraints, okay, and you end up finding these relationships. Okay? So for H plus, you get this. For HI, you get this. HMI, well, so for if you take H minus, that will be automatically 0 because either of the components, if it has a minus, it's automatically 0 because of the light cone gauge condition. So you find these constraints. Then you count your degrees of freedom. Okay, so that's what you have to do because now you have the constraints. I want to find out what are the independent degrees of freedom that you want to use. So you write it down. What are, after all these conditions imposed, what are the set of components there are? So you have plus I, which is 2 components, plus is 1 component, and ij has I think 3 components because 1, 2, and 2, 1 is the same. So from these constraints, you can eliminate these 2 guys and take Hij as the independent. Okay. Okay. So you write this thing then because this is independent. So you go ahead here and you see these terms drop off. Okay, because of tracelessness condition, this drops off. Because of divergence or transversality condition, divergencelessness condition, these two terms drop off. So you have only wave equation, and you write it for the independent DOFs, which is this. But here, as we said, we have three here. When I write it as Hij, there is one thing hidden, the 1, 1, 2, 2, and 1, 2. But because it's spaceless, which means that H11, H22 are not really independent. They are related to each other. So you have to pick one of them as independent. Okay. So yeah, so we are left out with 2 degrees of freedom. Okay. So then we define some complexified field made out of these two or 3 real variables, 1 plus 3, or I think 4 real variables. Okay. So here we did this so that we can write these constraint equations, and basically we'll be interested in this one, as you can realize, because this actually contains the independent UF. These are not independent. These were these guys which are dropped off because of the constraint relationship. So you see I plus is this one. So this can be explained if I consider this to be independent, Hij. So this is auxiliary to, as you can see that. This is also auxiliary, you can see, because this can be explained with I plus, which is itself can be explained or expressed in terms of these guys. So these two are dropped, and as you can see that. So basically this is to write the constraints, but mostly you'll be interested in this one, okay, which carries your independent UF. So you rewrite the auxiliary equation, okay, and the most interesting equation is this one. Okay, so these are 2 auxiliary equations that we saw before, and the wave equation for this thing boils down to wave equation for psi2, which can be written like this, as we saw just a few minutes back. And again, you apply the null reduction on salts of Korokshov et al. Okay, so apply this thing, and
Sorry again, what is M in equation 24?
which one? Well, M or N?
M.
N.
M. A-M. M.
Is it with I, or is it in the
mass.
it is the mass. M is the mass, if it is M.
So mass of what?
Mass of the particle.
But gravity is massless, isn't it?
No.
Because you wrote,
Yeah,
so if you
no.
look at your equation, if you go,
But I'm not talking about gravity. The whole point is I'm not talking about, okay, so linearized theory.
but
Okay,
Einstein
then
equation is satisfied only by gravity. There are no other fields which satisfy Einstein.
No, I'm not
equation.
satisfying.
No,
I'm not satisfying Einstein's
can I
equation.
add something? So
Sure.
at the non-interacting level, when you do not turn on cubic coupling, so on and so forth, at the free level, you can have as many spin 2 as you like. We're talking about the free theory here, right? Just a free spin 2 field without self coupling whatsoever. Of course, when you turn on interactions, things will change. Yes, you are right that Einstein theory will turn out to be the unique theory under certain conditions, of course. Yes.
So this psi is not necessarily Einstein metric. I mean, not Einstein metric, like space-time metric, right?
Well, you cannot have a metric in interpretation if you are talking about a free theory. You can, right, take Einstein Hilbert action, and then you have to linearize the theory by writing that your metric is Minkowski plus graviton fluctuation h mu nu, right? So if you like, this is the limit of Einstein theory, where we have sent the Planck mass to infinity, or we have sent the Newton's constant to 0. Okay.
Okay,
so
but
then you get rid of all the self interactions, and you will be left with just the free theory. Okay.
Okay, but still this free theory is not necessarily our gravity, right? Because of mass term.
We are that again. We are doing it.
Let's go back and see where the mass come from. Can you go back a bit, please?
So I can go from the front. This is Einstein's theory from the beginning. We do the light cone gauge fixing, and we have come to
Yeah,
this
so
point.
there is no mass. So stop, please stop. Just go a bit up.
Yeah.
Yeah, so equation 18 is basically linearized Einstein gravity, and that's basically gravitational wave propagating according to Einstein theory. Like equation 18, it's just wave equation without any mass term. Okay, now how does mass arise in this theory now?
So mass arising so mass doesn't arise that level, right? That's true. In 4D here, the massless theory, but then we're dimensionally reducing. We're doing a dimensional reduction here. Just we did for spin 1. The photon is massless. So why there was no objection in that case? We made photon massive here, right? If you think about it.
So I think it might be useful to write down the answers of null reduction, right? You basically have to assume that I think you showed it in the very beginning, right? You have an answers for the field. That field is some function times an exponential function where the m.
Okay, thanks, I got it. So it
shows
was
up in the
ansatz that
yes.
we impose.
Yes.
Okay, thank you. Okay, thanks for clarification. Okay, please continue. Thanks.
Thank you for the question. I'm sorry. It could have been much clearer, I think, but okay, I'll try to do better. Okay, so yeah, I hope everything is visible, clear. So that's the story for spin 2. Okay, so so basically have the box is going to act on the independence. So this is as you saw, these terms drop off, and you only have this. This is for the independent TOFs, and you write it down this way because of light cone coordinates, and for the independent complex TOF, and then you use the ansatz, which gives you the mass term, and then of course you can express the auxiliary equations, but we are very interested about this term, so I'm just going to skip these things. These are for formalities. So you just focus on this term. So you just again plug this in. So d minus phi 2, you plug this in there, and you end up getting Schrödinger equation. So that's the story for spin 2, and it's a planar Schrödinger equation because it's a 2DOF in a complex setting. So so the question, so your question would be is that where is the non-relativistic limit here? So can anybody tell me where is the non-relativistic limit here? If you want me to scroll at a particular page, I can go. But tell me where is the non-relativistic limit here? Let's start from here. It turns out this is the non-relativistic limit actually. It's not just some dimensional reduction, you are also doing the non-relativistic theory at the same time. So by reducing the dimension and bringing the mass and ignoring one of the propagating coordinates and the dependence of psi on that coordinate, you're essentially going to a non-relativistic regime. So that's the limit.
So I think here it might be useful for the audience to go back to show how that's done for spin 0. I think you have shown it before, but this will be good to show it once again, right? That you take this ansatz and then you take the limit. So all terms that go like 1 over c or 1 over c squared, they drop. Yeah.
That's the idea. Okay, and any questions? Please ask me questions if you have any. So there is a spin 3 story now. So this is something. So this part is done by Berkshire. Now, this is a bit not trivial version. Well, it's actually not that hard. We can just start with the Fronsdal equation for massless totally symmetric massless totally symmetric spin 3 field. This is the Fronsdal equation. You can just take it from a higher spin reference, and then you go ahead and do the light cone gauge fixing condition. Okay, so you find this. So you can write down the components, and because you want to really do calculations with components, you just want to know what kind of components you're looking at. So your light cone gauge condition is always with a minus there. So you have this many light cone gauge conditions. Then you do some, reshuffling, as we saw, that you combine them in some complex fashion and write it this way. So what is the important thing is that that I want to emphasize here is that, okay, so you have to, so after imposing the light cone gauge condition from the equation of motion, and this condition will lead you to two, which I have not actually explicitly shown here, which will lead you to two constraints similar to this. Sorry, I haven't shown that there, which will lead to these two constraints. Okay, so these are also the same constraints that one gets in the Fierce-Pauli program. Okay, so in the Fierce-Pauli program, Fierce-Pauli program, so one has so these are arbitrary spins, integer spins. So this is the dynamical equation, which is the Klein-Gordon equation. Then one has the transverse condition, and one has the okay, so I should say, so mu1, if it's the mu1, then this is minus 2. Okay, so this is the Fierce-Pauli, these are the Fierce-Pauli conditions. So this ensures that you get the right degrees of freedom, okay, and your theory is consistent. So we are essentially finding these constraints every time for every field. Okay, so every spin, it could be spin 1. For spin 1, we don't have the trace, obviously, because we do not have enough indices. For spin 2, we saw we could accommodate both. For spin 3, we'll also have these two constraints, okay, coming out from light cone gauge fixing. Okay, so one uses the light cone gauge fixing, okay, together. So with equation of motion, one recovers these constraints, okay, and these help you to identify the independent UF. Okay, so that's basically the algorithm for all the other spins. Okay, and you know that you will get 2 degrees of freedom for sure. Okay, so you do this procedure and you know that you will get 2 degrees of freedom, and you identify that 2 degree of freedom, okay, and then you complexify it, okay, some some indices here depending on which field you're considering. If you have spin 3, there will be 3 indices, so maybe 111 or 112 could be, okay. And then,
excuse me, I'm slightly confused here. Are you working in three dimension now or four dimension?
I'm still in 4 dimensions.
So you are in 4 dimension and you have a mass term, right? I see that
No.
you are working with massive fields, and then you are talking about two degrees of freedom. It's a bit confusing, I would say.
Sorry. Yeah, I'm sorry. Yeah, I shouldn't have. Okay. This, okay, sorry. So okay.
Maybe I can help you. So what was the point that you were trying to make here?
I was trying to make the point that
are you working with massless fields in 4 dimension or massive fields?
Massless fields.
So the count of degrees of degrees of freedom for massless field is slightly more subtle, right? So you have the Klein Gordon equation, but you do not have the divergence constraint. So it's more complicated than that, right? So you have a doubly tracelessness condition which kicks in from spin 4. So for a massless field, the spin 4 field is doubly traceless, and it's also symmetric. Okay, and then you have gauge symmetry, and the gauge parameter is traceless. So symmetric and traceless, and that's how you can prove that in four dimension a massless field has 2 degrees of freedom with spin one or larger. Yeah, bosonic field. Yeah.
Yeah, I'm sorry. So yeah, okay. Okay, so I wanted to say that the light cone gauge condition together with the divergence conditions and the traceless condition helps one to identify that UF, independent UF. Okay. So because of this, there is a light cone gauge condition.
Once again a bit confused. Where do you get the divergence condition for massless fields, please? It's not clear to me.
This is here. Equation 12.
So that's what you mean in the light cone coordinates. Okay.
Right.
Got it. Okay. Thank you.
Yeah. So that's the idea that we're going to use for spin 3 and for spin 4 and everything else. So for spin 3, you can do the calculations, and I apologize that I did not write many details of those things. I just wrote the light cone gauge condition. I did not write these constraints here, which should have done. That's why I have to come back here and tell you that this is the case. So yeah, okay. So you have to just do a bit counting of the components. So how many components there are, and how many light cone gauge condition sets to 0, and how many divergence lessness condition and tracelessness condition sets to 0. So, and from these auxiliary equations, how you can actually identify 2DUFs. And once you have 2DUFs, okay, once you have correctly identified the 2DUFs, you can actually go back to the ansatz and just use the ansatz, and that's it. Any questions? So I wanted to, I got very much carried away. I was completely wrong for writing this program because I was not considering a massive field. I was trying to actually hint at these two consistency relationships, but they actually require you to consider a mass term for the Fierce-Pauli program, which in our case, light cone gauge condition combined with these things actually does it. But there is a similarity, but not exact similarity because it's massless. Anyone confused and any questions?
So I think it might be instructive to mention that, say, in equation 37, you have nebula delta minus, right? And minus is called the light cone time. So when you take the light cone coordinates in the light cone coordinates, you can pick up the physical degrees of freedom, and you see that one of the coordinates is redundant, and you drop that, which was the plus, and the remaining coordinate is called light cone time. Yeah, so in this sense it's is the time variable actually, right? So you see that equation 37 now leads to 41, right? Something like
Yeah,
that. But
yeah.
I have a question. In 41, how many fields do you have?
I have two fields, two real fields.
So and why is that? Because psi is complex or what?
Yeah,
So
psi is complex.
what does this n means? N 1, 2, 3?
Okay, because I have a number of psi's. Some of the psi's I want to use to write the auxiliary equation.
Yes.
And third one is the one which gives me the Schrödinger equation.
So psi 1 and psi 2 are not dynamical fields, right?
No,
In
So
in
you can
that
see
sense.
psi one is expressed in terms of psi 2, and psi 2 is expressed in terms of psi 3. So ultimately, psi 3 is independent, true independent DUF, complex DUF.
What is this psi 3? Can I have a look?
Yeah, sure.
Yes, so the point is that any field that has a that has a component in the light cone direction plus is a non-dynamical field. So basically 31 and 32 are non-dynamical. What turns out to be the only
you're right.
relevant dynamical field is 33, which does not have any of the components in direction plus. Okay, thank you.
Yeah, I just want to mention, so it's absolutely right, just minus actually, sir, not plus. But we are taking plus to be the time coordinate. So we're considering the light cone minus to be spatial coordinate. The choice, everything else. All right. So, okay. If there are no questions, I'm going to just go ahead and describe the Lagrangian density approach. Is there any question? So this approach you can generalize to spin 4 and others. Okay. That's good. So now I'm going to talk about the Lagrangian density approach. Actually, okay. So I think I missed a bit again. I can't talk about Lagrangian density approach before I show that it works for fermionic things. So again, I apologize for me being a bit fidgety. So I haven't talked about fermionic high spin fields at all up to this point. So spin 0, spin 1, spin 2, and spin 3. So fermionic high spin fields is a novelty in this sense. So what Barkshoff and et al., the collaborators did, they actually mentioned they did it explicitly for spin 2, and they did it for spin 0, and they mentioned that their method can be generalized to arbitrary high spin bosonic fields. So they didn't do a spin 3 case, which was new, and in our paper we argue that this can be generalized according to the this protocol that I was trying to mention, that you use this algorithm, you use these conditions, and you find out the right DOF. Do the counting, and you see that this turns out to be the right counting for right auxiliary variables. Okay. So that's the story for high spin bosonic fields. Okay. What about high spin fermionic fields? So they did not consider high spin fermionic fields at all. So we are going to consider it. Okay. So the first thing you would ask, what about before going to higher spin, as we consider spin 0, the simplest fermionic field is spin half. Okay. So what is the case for spin half? So spin half is the Dirac equation, is the Dirac spinner. Okay. And you consider the massless Dirac spinner like in 4D. Okay. Dirac equation in 4D. Okay. And because it's a Dirac equation, it automatically satisfies the Klein-Gordon equation. Okay. And it has 2 DOF. And then you again do the business of dimensional reduction. So let me write it again. And then you find similar equations like spin 0. So essentially, there's a story. Okay, for spin half, you just go ahead and do it, and you find the Schrödinger equation. Okay. Now, what about spin 3 half? What's the story for spin 3 half? So again, one has to start with the massless spin 3 half, which satisfies the Fronsdal equation. Okay. The Fronsdal equation for massless spin 3 half field is given by this equation. Okay. So then this is our dynamical equation. I'm calling it equation 1. Then you impose a light cone gauge. So you work in light cone gauge conditions. So somehow you can say my coordinates changed. Apologize. Sure. Okay. So what is spin 3 half? Okay, you might be confused what spin 3 half really means. Spin 3 half means it has a vector index and it has a spinor index as well, which I am suppressing. Okay. So the vector index represents for the space-time vector, and the alpha represents the Dirac index. Okay. The spinor index. The light cone gauge condition amounts to saying that you have phi minus equal to 0.
Sorry, I have again a naive question.
That's all right. Yeah.
So why, I mean, how does gauge comes in spin 3/2? There is no gauge field here.
There is a gauge. This has gauge symmetry. This has a gauge symmetry because there is a Schroedinger field, and it is given by the spinor field. So there is this. Okay. So there is this epsilon. I think it goes something like this. So as similar to this. Mu lambda or something gauge symmetry.
And what is it?
There is. So this is spinor field. So there is spinor freedom here. There is a gauge symmetry given by this.
Well, the epsilon is not a field; it's a gauge parameter.
Gauge parameter. Sorry. Yeah.
I should have field. Yes. So yes. So actually, you have gauge symmetry for any spin larger than half, right? So just like for spin 1, you have a gauge symmetry. It looks exactly the same for spin 3 half, right? It's just that the gauge parameter in this case is a spin half gauge parameter, not spin 0. Yes.
So maybe my question is more naive. How do you know epsilon is actually a gauge field?
Not a field parameter.
Well, just like how would you say you take the equations of motion of this field, and so let's go back. How do you know that Maxwell theory has a gauge symmetry, right? It's exactly the same. You plug in some transformation and you realize that it does not change, right?
And you can do the same for this Fronsdal equation.
The Schroedinger equation. It's actually right. Okay, yeah.
There is this Fronsdal for spin 3 half. For spin 3 half, the equations of motion can be written in a simpler way, which makes the gauge symmetry manifest. But yes, so you can prove it.
So
Yes.
if I put this psi bar in equation 1,
Yes.
then what condition do I need on epsilon to prove that this equation is invariant under this transformation?
So just to plug that in, that you, and you see what you get, right? So what
Yeah,
what do
probably
you
help.
get when you plug that in?
Yeah,
You
okay, I can probably.
see that all you have to do is that d slash commute with d mu, right? That's all, and
Yeah.
which is true, right?
Yeah. So one can write this thing in this way as well, which manifests. We should manifest this.
This is manifest. So just a bit, please go up. Please go up. And here, when he writes in line 1, 2, 3, EOM, this gamma mu nu rho is an completely anti-symmetric gamma product. Okay, so when you have del nu, and then the transformation goes like del rho. So del nu and del rho, they are symmetric with respect to nu and rho, whereas gamma mu nu rho is anti-symmetric. So this will be 0, right? But here it's manifest at the level where he showed. Can you now go back to where you were? So here, let's plug in, right? So let's plug in this transformation, and the first term gives you d slash d mu, whereas the second term gives you d mu d slash, right? And you see that they commute, right?
Right. My question is that, like, for connection, it has a particular transformation property, like it must transform like a connection 1 form. That's why it's called, actually, in physics, gauge field, and in maths it's called connection 1 form. So my question is more precisely, does this epsilon transform like a connection 1 form or like a gauge field in physics term? Do they
Actually,
have
you're
a
talking
transformation?
you're talking about psi. I mean,
Sorry?
mu.
Yeah, I think in physics, that gauge symmetry is a more general idea. It doesn't have to transform in some specific geometric, like like the way mathematics you are saying. A gauge symmetry is simply just a redundancy of description, and it can have very general forms.
So the epsilon is not then like the connection 1 form, just it is something which keeps equation 1 invariant, right?
I am not sure, but I don't think it has to be. But maybe I think either Abhijeet or Rakib will know the answer, right?
What is the question once again? Sorry.
The question is epsilon a connection 1 form? And I don't think it is.
No, it's not. Yeah.
Okay. Thanks. That was my question. Thanks.
And in fact, Anirban, the epsilon here is the analog of lambda, and lambda is not the connection 1 form either.
Exactly.
Right.
Exactly.
And
Exactly.
I mean the partial derivative of epsilon, right?
the partial derivative of epsilon is just a change, in the gauge field. It is a change in the gauge field, right? So I guess, what I'm saying is, yeah. So epsilon is, I don't think that here we have a spinner, right? Not a spinner vector, really. Yeah. So yeah, I don't think the geometric analogy is very precise here. I'm sure people have done work on it.
Psi can be rendered a 1 form, right? By multiplying with the gamma, but
Right.
epsilon cannot be. Yes.
Okay, yeah, that's not clear now. Thanks.
Okay, very good. Thank you, everyone. Okay, so we have the
Sorry,
Francois
Abhijeet, for
equation.
taking over your seminar. I
No,
apologize.
that's wonderful. No, no, my God, no, definitely not. I didn't expect, and this is so much surprising. I'm really very emotional. Okay, sorry. Thank you so much for your input. It's educational and inspiring. So I have the Francois equation. So we have the Francois equation here, and then we impose the light cone gauge condition. Okay, so necessarily that drops off. Okay, this term, and you end up having. If you write it for psi minus. Okay, so if you write it for psi minus, so I'm writing this equation of motion for psi minus, and then this drops off, and you end up finding this equation. Okay, you don't want your psi to not depend on m, so necessarily you demand that this thing should be 0, which is your constraint for gamma. So this is okay. So what does slash mean? It means this. So this is another constraint. So you have now 2 constraints. So now you can actually excuse me for. So you can actually get another constraint. So you can actually get another constraint. So you can get another constant if you take a divergence of this equation. So you see from equation 1, if we use constraint equation 3, okay, so this term will drop off, and we'll have d slash psi m equal to 0. Okay. And then if you take a divergence of this equation, so you'd have d slash of d dot psi to be equal to 0. Okay, from which you recover this thing is another constraint. So there's another constraint. Okay, so you have now a bunch of constraints. Okay, so let us do a counting. We had psi m alpha. So alpha represents, say, one complex DF. Okay, and m has I'm 4D. I'm in 4D. So I have 4 real DF. So now let us do counting without considering this alpha, because psi appears everywhere. Okay, so this alpha is everywhere. Okay, so let us only consider the real parts. Okay, which is the 4 here. So I have one constraint coming from light cone gauge condition. I have one coming from the gamma tracelessness condition, and I also have one coming from the divergenceless condition. Therefore, I'm left out with one real DOF. And this one real DOF multiplies with this complex DOF one, which is in terms of real should be 2 DOF. So therefore, I end up with 2 degrees of freedom. That means one psi component, which could be psi 1 alpha. So I write down.
Abhijeet, I have some comments here. I think with all due respect to you, you just added and subtracted some random numbers to get to, and I don't see how you do that counting, because you start with a massless field, right?
Right.
Is that right?
Right.
And here I am slightly lost with the massless field. How do you get the divergence constraint? So once again you are working in the light cone gauge, right?
Right.
Okay, now that's why it gets a bit confusing. So when you write the gamma m psi m in the next yes, in equation 3, that is already in light cone gauge, right?
This is in light cone gauge.
And when you go down, when you write this divergence, what do you mean by that, to be precise?
So d plus, psi plus, d minus, psi minus, and dive. Okay, so di psi I. Okay, so this is what I mean.
Now the next question is, when you count the degrees of freedom, can you go down a bit?
go down. Yeah.
Now you said that m has four different values. It's a Lorentz index, but alpha has four as well, right? But
It's a
alpha is a Dirac.
massless Dirac force.
Yes, but alpha runs from 1, 2, 3, 4. We know that the in four dimension the Dirac matrix has four dimension, right? So why you say it? So naively to begin with, there are 16 degrees of freedom, 4 times 4, not just 4 times 1.
No,
Yeah.
okay, the psi, okay, when I'm considering 4, we're considering m, yeah, you're right. But I'm considering m separately than alpha. So psi alpha is everywhere.
Yes.
Okay, so I'm not really considering about psi alpha component.
So then when you say two degrees of freedom, it should be two times 4, which is 8, right? So it means that you need to get rid of more. Yeah.
Well, it's a okay. So this story should be the same for Dirac spinner. Okay, so we know that in 4D Dirac spinner, if it's a massless Dirac spinner, that's a wild spinner. Even though I'm saying it's a Dirac spinner, it's actually a wild spinner. Does it make sense?
Even while has the alpha values, they run one and two, right? So
but it has 2 DOF, right?
Anyways, I don't want to kill your time, but I think that the counting you are showing here is a bit fishy actually. But let's go ahead.
Okay, but well, my point was I was actually banking on the wild spinner, so I'm not really doing anything with the alpha. Wild spinner has 2 DOF. That's what I was banking on.
No,
okay,
you are assuming that the value of alpha does not run. Well, it does. No matter whether you take Weil or Dirac, right? Alpha
no, I think that's what the 2 comes in the last line. The 2, he's counting the wild spinner values. So so I think what Abhijeet is trying to do, he's not touching the spinorial degrees of freedom. He's just assuming them to be wild. Is that, and then he's just basically cutting down on the vector degree of freedom.
Thank you for the clarification, but I don't think he mentioned this, right? So that's why he really got confused actually. Yeah, thank you.
Thank you, sir. Yeah. Okay. I'm sorry. I'm very sorry if I messed up. I hope that
don't be so apologetic.
Is there any questions from the audience? I'm hearing questions from the experts, but audience should have a lot of questions because experts have a lot of questions. If you're confused, if you have a naive, there is a naive question, but if you have any questions, please ask. These questions are, this is a research talk, so if I mess up, if your question will help me to get it right. Okay, so if there's none, then okay. So as I was saying, that if you can identify which so you have this constraints, and you have identified one component to be independent. Okay, you can choose to be, so you can choose m to be 1, 2, plus, minus, whatever you want to, because really it doesn't matter as long as you have the proper. Well, it would matter. Okay, it would matter slightly. Later we'll see why it would matter. You want to choose actually these things. Okay, they don't have any. Okay, you want to choose actually these guys, psi1, psi2, because they don't have any C factors. Okay, so we will see why that's important, but okay, in a while. Okay, so let's choose 1 alpha to be our independent. So our dynamical equation was, let me show you again what was our dynamical equation. So I had this Fonsdal equation because the fact that I have a gamma tracelessness condition. So this actually drops off. So I have one dynamical equation, okay, which is d slash psi m. And so I'm writing that for this independent UF. So this is a Dirac equation, and the story goes, because it's a Dirac equation, it will satisfy the Klein-Gordon equation, and therefore we can do the same ansatz, and we can use the same ansatz because the box can be written as d plus d minus psi 1 alpha. Here you have d square psi 1 alpha. So then you go ahead and apply the Nernst reduction for this one, and that's it. So then you recover the Schrödinger equation for spin-3 half field. So that's the idea, and this is the same idea you can use for spin 5 half and thereof, and so on. Okay. So the ideas are again the same, but slightly different for fermionic fields, because instead of tracelessness, you have a gamma tracelessness. Okay, because there is no mate. Okay, so eta do not work for eta is working for phi. Okay, is replaced by gamma for fermions. Okay, so that's the only new bit to the story. But actually, this is one-to-one with the fact that you have a traceless symmetric field for boson, and you have gamma traceless symmetric field for fermions. And the arbitrary higher fermions are actually found from this prescription. So you do not touch the half, and you start increasing the integers. So if you put n equal to 0, you have Dirac. If you put n equal to 1, then you have spin 3 half. If you put n equal to 2, you have spin 5 half, and so on. So essentially the same algorithm goes through. So that concludes my discussion of the equations of motion approach. So there is another approach that one may try to consider, that is the Lagrangian density approach. So we know that Lagrangian is more fundamental in a sense, in a theoretical sense. Okay, so we worked from the equation of motion. We had to use someone else's research again. So Fronsdal equation, who worked out for arbitrary higher spins what should be their equation of motion depending on gauge symmetry and every other constraints to make a sensible equation of motion. So use that, and okay. But now you might say, okay, but you can find the equation of motion from Lagrangian density, right? So that's the idea. So here I'm going to work explicitly. So here one point to mention: in this approach, I'm going to work explicitly in 3 dimensions. Okay, so there is no dimensional reduction in this approach. Okay, that's one thing. And okay, good. Okay, good. So I'm going to use projectors. There'll be transverse traceless projectors. Okay, these projectors can be constructed in 3D by the general symmetry arguments of SL2R. Okay, so Lorentz group is SL2R in 3 dimensions. Okay, so this is isomorphic to SU11. Okay, and the little group which sits in SU11, the Lorentz group, is U1. Okay, so okay, interrupt me here if you have any questions. So this U1, under this U1, okay, I haven't gone to spinors because I will first talk about bosons, but just I want to mention what the spinor case here is. So here you'd have 2 helicities. One is the positive helicity, one would be the negative helicity. Okay. Okay, under this little group. Okay, so you have 2 helicity modes. So you can say it is psi plus, and you can call it a psi minus. Okay, in 3 dimensions. Okay, so therefore you can construct phi plus projector which acts on your psi and gives out the positive helicity mode, and you have a phi minus acts on psi and gives out the negative helicity mode. So the idea so this is the work of Puzenko, okay, et al. So I'm very sorry I haven't mentioned the archive links here, but you can search about Puzenko 3D projection. 3D projection, if you search in Google, you can find his paper, 3D projections of projection projectors instead of projection. I should say projectors for higher spin fields. Okay, and similarly, you can write Barkshoff's work. You can find the Barkshoff's work by writing 3D spin 1 field and spin 2 field. Okay, if you write these keywords, you'll find their papers on the archive which I used in my talk. Okay, so here this is the work I'm using. Kuzenko, okay, and et al. Have constructed these explicitly constructed these projectors. Okay, so here they used these group theoretic arguments, and from there they were able to. So because of the little group, you know that it keeps the standard momentum. So this is a 3D massive theory I'm going to consider. So this is 3D, that means it's a massive theory to begin with. Okay, so the massive theory, okay, so the little group in that case would be SO2. Okay, so what he did is he considered the little group representations, and from there he was able to get these helicity modes, okay, for positive and negative helicity modes. And from these two helicity modes, he was able to construct. So you can construct from the spinors anything. Basically, you can construct vectors and tensors and everything. So he was able to show that from these plus minus basic projectors, you can actually get projectors for vectors, for spinor, for vectors, for spin. Okay, so these things that I considered here, fermions, they are actually, you can consider them as spinor tensors. Okay, so Radhika Schwinger or spin 3/2 was a vector spinor. But spin 5/2 would be an example of a 2-rank tensor spinor. Okay, so you can construct the projectors for them. Okay. So with this remark, so let me show you how it works for spin 1. Okay. So for spin 1, the projector that Kuzenko constructed is this. Okay. So this is one over the box, and these are the off-shell projectors I'm using. He also constructed the on-shell projector, so I'm using the off-shell projector, okay, to begin with, okay, because I am not using equation of motion. Okay, I'm going to derive the equation of motion from the Lagrangian. So, okay, so this is the projector.
Sorry, I have a question. What do you mean by 1 by box?
Oh, box is a D'Alembertian.
But it has a non-trivial kernel. How can you divide it?
It's off-shell. Okay, and it is okay. It's off-shell first of all. When it's a non-local, that's how I say it.
No, but an operator option. What do you mean by off-shell operator?
Off-shell means that it is not okay. So it is not okay. This field, whatever this is going to act on, that field is not going to satisfy equation of motion.
Yeah, that's okay. But this is D'Alembertian, so it's so if you look at it has dt. If you are using coordinate, so dt square minus dx square, right?
Yeah.
Yes,
okay.
and now you see that there are non-trivial elements in your domain for which this will maps to 0. So you can't divide an operator which has a non-trivial kernel like a matrix. You cannot divide a matrix unless its determinant is non-zero, right?
Right. So okay. So when is this going to be 0?
When you have light-like covectors. So in your light cone, this is 0, right? In your light cone, this is 0.
Yeah, but I'm considering a massive particle.
Yes.
Okay. So if I have a massive particle, so you
I think he's restricting the domain, right? That's what he's doing. He's restricting the domain.
No matter it's massive or massless, your domain always contain light cones because it's a relativistic theory, no matter which particle.
Yeah, even massive theory, if you have, so you're saying basically this equation, right?
Yes. So even massive theory has the same domain of light cone.
If you use the equation of motion, okay, so if you set it to 0, I'm not setting it to 0. That's the meaning of off-shell.
No, it's not setting to 0. Box cannot be 0. Box is an operator. An operator cannot be a 0 operator.
No. You're missing my point. Not acting on. Okay. the box acting on psi is not going to be equal to 0.
Yes,
That's
but
my
psi can be
concept.
like in your light cone points of psi, box will always give you 0 because of precisely this form of box.
But okay, so
so
okay, so
maybe
let me
I should
okay,
put it simpler way.
okay.
Your box has 0 eigenvalues, right? If you look.
Okay, so if it's a massive theory, this should be something like this, right?
I mean, depending on your theory. So it's a Klein-Gordon equation, it's massive. Okay, yes.
Yes, so it is not 0 for psi.
So I have a question there. Are you working in flat spacetime or anti-de Sitter?
No, not at the it's
It's Minkowski. So
yes. So if you are working in Minkowski, then the complaint is valid, right? You cannot write. Well, you can. Then it's a non-local projector, and it's
non-local projector, non-local.
Yes. And then it's non-local in time. And shall we trust this result or not?
Absolutely not. You have 0 eigenvalue. You can't divide anything by 0. Just think about a matrix. If you have 0 eigenvalue, you cannot divide.
Well, you can. It's just that this thing is not a local, right? So what
Yes, it is not a local operator, but
yes, what
not even defined. 1 by box is not defined.
Wait, when you are saying that 1 over a box cannot be inverted, you are saying that under the assumption of locality, right?
No. So 1 by box is a pseudo-differential operator, and pseudo-differential operator are never local operator. So we are not assuming anything. So just what is definition of 1 by box for you? Just write the definition. You will see the problem. So it's an operator which maps some element of your domain.
So can I say something? So, look at the massive equation that that Abhijeet is writing there. So, we have box minus m squared acting on psi equals to 0, right? Mm-hmm. So that's kind of what we call a Klein-Gordon equation, the free Klein-Gordon equation. And what we call the Feynman propagator is essentially the inverse of that wave equation. Mm-hmm. And obviously, that's a hyperbolic equation.
Yes.
And therefore, it's not well defined. Inverting when we write down the the Feynman propagator, the propagator, not the Feynman propagator, the propagator is not well defined, and that's connected to what
exactly.
You're saying.
It's the same problem. It's the same problem.
So how do we get around it? We say that, well, the solution of this equation, that this is not a well-defined object until I specify what the boundary condition is. And how do we
changing your
the boundary condition? We choose the contour on the Fourier space, contour integral. So here we basically have to do the same thing. That operator, what delta, that is not well defined, but there is a boundary condition that is implicitly choosing to make that well defined.
Yeah. So you are choosing a boundary condition so that you get rid from your 0 eigenvalues.
Yeah. Well, that was the question. Okay, so that is the concept.
Thank you very much.
But I think that then this 1 over box is just the massless limit of the Feynman propagator, which is once again brings back the problem. So I think still the question is valid. So the answer is that the definition of 1 over box is such that when you multiply both sides by 1 over box in the last line, you get psi equal to m squared 1 over box psi. Okay, so it is the invert of that. And how you find it? For sure, you cannot invert that if all your functions are local. So I would say that this 1 over box to find an expression for 1 over box, you cannot assume locality. So,
So what's your definition of locality?
locality means every locality means that the equations of motion are not integral differential. Yeah. So here we have just the differential equations, right? So when we have to do integration also with respect to space time, then it's non-local. Yeah.
Okay, I don't know about this notion. So in partial differential equation theory, there is something called non-local differential operator. So
Yes.
let's take a Laplace operator, okay? Our favorite operator from physics, from electrodynamics.
Exactly.
If you invert
Exactly.
a Laplacian, then it's called a pseudo-differential operator.
Exactly. So
And
that's
a
the same.
pseudo-differential operator, no, these are not same, because pseudo-differential operator is defined in a non-local, in a different context. It's defined in terms of, not in terms of integrality, rather it's defined non-local or pseudo-local in the sense of its reference set or support. So these two notions are not directly same, but you cannot use the same process as you do for Laplacian for a box operator, precisely for the reason Tibro sir has mentioned, because it's a hyperbolic operator. So either you have to specify boundary conditions such a way that you get rid for your zero eigenvalues, what we do for Feynman propagator by I epsilon prescription, which is same as telling that we are changing its kernel, basically equivalent. Or
That is right.
or you can do another thing, that you can define your Green's function without as the inverse of this operator. So you are not really inverting, rather you define some operator, say G, which acts on your box and equals to 1.
That is right. So my point is that I don't exactly remember the Kuzenko. I believe that they assumed the I epsilon thing, but I'm not sure. Yeah.
Okay,
So
if it is I epsilon, then it's basically what Tibro said.
Yes.
And then
Yes,
Right.
but
Ultimately,
I'm not sure if they have the I epsilon part. Maybe Abhijeet can say, right? I don't think that they have it. Yeah.
yeah.
okay, maybe
Yeah,
we can go on. We can talk later because it's already over time. So I should not ask these tangential questions right now.
this is a great question. Yeah, so I think it's okay. So this subtle point, I don't think. Okay, so I haven't seen Kuzenko used it, but as you have mentioned, to make sense of this thing, we have to use boundary conditions. Sir has finely pointed it out where both of you, all three of you, have finely pointed it out that where the problem is. So I'm moving on. Actually, excuse me on my lack of knowledge here. So I was on the projector. So you see the projector, and then I'm going to apply it to the spin one field. Okay, should be psi. Should be some. Okay, so I'm going to call it same thing, phi a, and you would end up getting something like phi a minus. So these boxes will, to cancel these boxes, as I was saying, that they cannot have zero eigenvalues. Okay, so d a d dot h divided by box. Okay, good. So yeah, let's go h, go phi. So okay, good. So this is what one gets if one applies this projector, transverse stateless projector. Oh, well, in this case, transverse because it is a spin one field. So okay, so one from here one can immediately. So I'm going to call this phi transverse. Okay, and one if one calculates, one sees that this is zero. Okay, so therefore I get this divergence less condition. Okay, So I have 3 DOF. I have 1 constraint, so I'm left out with 2 DOF. Okay. So what's next? Okay, so next is the Lagrangian density question. So the Lagrangian density comes out with these factors. So this is for spin 1 field, FABT, T minus square root minus determinant eta. So it's a massive field. Phi a t squared. And after doing some component calculations, one will end up getting this result. So there'll be C over 2, and one gets okay. So one gets minus 1 over C squared. So this C comes from this. So eta, my eta AB is minus C square 1 1. So therefore one gets C. So I'm going to break it down to its components. Okay, forgive me for my H and phi naught. So because of my notes, H. So one just has to do the calculations, straightforward calculation to find this expression. Okay, good. So one can heuristically see what's happening. If you have not components, you should get 1 over C, because these are actually, so what's happening is that you have eta AB, which is the inverse matrix. So whenever I have eta naught naught, you'd get a factor of minus 1 by C squared, 1 over C squared, yeah. Okay. So there is 2 0. So you get eta naught naught. So you get 1 over C, minus 1 over C squared. So that's the factor here. Similar factor here. There was a minus. So this minus gives you a plus. And these things do not have this 1 over C squared. So that was the point that I was trying to mention. When you're trying to figure out the right DOF, it is important that you choose the DOF which does not go to 0 as you take C goes to infinity. So here you definitely do not choose phi naught. Okay, so you want to get rid of phi naught actually here, precisely because of this reason. And there is a C appearing here, overall C, that you send to the left. Okay, so that it becomes C inverse the Lagrangian density, which if you take C goes to infinity, this goes to the non-relativistic Lagrangian density. Okay, good. So as I was saying, that we have a constraint here. Okay, this is the constraint. It's one constraint, so I can solve this constraint. Okay, for phi naught. Okay, so I will express phi. I will express phi naught in terms of phi I. Okay, so therefore this is an auxiliary variable. Okay, so I can just drop this variable from the equation of motion, okay, by substituting its equation of motion, because it's auxiliary and I can always express it in terms of phi I. So I will left with phi I transpose box minus MC square phi I transpose. Now it's easy to see that this equation of motion is nothing but phi I transpose. Okay. And this is nothing but a Klein-Gordon equation. And okay, so if we have a Klein-Gordon equation, okay, you can always get, but here we have a bit of non-triviality, because this is completely real here for this moment. Okay, till this moment is completely real, but as we do always, we break it down. But actually, I kind of can do better than this. Again, please excuse me here. I can do better than this. Okay, I mean directly Klein-Gordon equation jump na korte pari. The whole procedure actually, you can say that this is okay. Lagrangian density approach, I came from this Lorentz theory to still it's a Lorentz invariant theory. Is it? Well, okay, but I'm taking C goes to infinity, but let me not take C goes to infinity here. Okay, let me not take it. Let me do something more, something better. Okay, so I can do better than this. So what can we do better than this? We can again break this up. Okay, we can again break this up, and we will have there was a half there. I missed. Sorry, there was overall half there. So there was this thing. So dt square phi I transpose plus 1/2 phi I transpose dI square, so I should say dj square, some other variable, phi transpose minus half mc square phi I transpose square. Okay, so I'm just rewriting this in terms of components, and now I'm going to define a complex field. So let me call my complex field capital Phi, which is nothing but phi 1 transpose plus I phi 2 transpose. Okay, remember my I is 1 and 2. So with proper normalization, so then my C inverse of Lagrangian becomes 1 over C squared if you do this thing. So there are two terms here. Okay, so you can combine them. Okay, by using this phi, and you can write the time derivative square. Okay, so you can do one thing, you can make it a plus, you can do integration by parts here, and you can write this like this. Therefore, it's a square. So you can write it as a complex field time derivative mod square. Plus, you can write this bit as this. Okay. And then you can write the last bit as just the norm square of the complex field, essentially. Okay. So rewriting this way. Okay. Now still not going to take. Still, I'm not going to take C goes to infinity. Now we can do more. We can do more. We can, as Saqib sir was mentioning, that we can do this thing. Okay, because it's a projective representation in 3 dimensions for massive field. So we have a complex representation for complex massive field. So we can do this. So I suppress this actually here as well. They're always there. So you plug this in there. Okay. And then what you get is 2im. Now, okay, after plugging this in, you'd have this term. Okay, so this is a nice bit calculation that one has to do, is that one would see this c square, one of the c square terms will drop off, they will cancel out. Okay, essentially these terms will also drop off. If you substitute this, you can easily see that this term will come out that the c to the power 4, one of the c to the power 4 will be cancelled by one of the c squared, so that will cancel this term, and this term will become this term, and there is a mod square there which will pick out this term actually. So now at this level you take c goes to infinity limit. So this part is completely finite. So you can say it is immune to non-relativistic limit. This is the mode that survives the non-relativistic limit. Therefore, essentially this is the same thing. So now if you apply Euler-Lagrange equation, you don't rely on Klein-Gordon here. You apply Euler-Lagrange, you get the with h bar factors, you get the Schrödinger equation. Okay, so that's the story for spin 1, and the same story one can write. So this is a simple. So why spin 1 I did all the time? Because spin 1 you can see clearly what is happening. For others, you can do the same calculations with the projectors. The calculation will be a bit more messy. You have more components, but the story will be the same because it's an algorithmic approach. What I have done, unless you hit some subtleties. Okay. So here, as you can see, there are actually, I try to mention that there are no subtleties.
Can I ask you something? Where here have you used the spin projectors? Sorry, I missed that part. You must have used it
at the front. I
Yes.
always work with the projector.
I have just checked the Kuzenko paper, and I don't think they have the I epsilon. Okay, but we can talk about it later. I think that one can find a solution to it which is not local. As long as you impose something local, I think there is a problem, right? So, but we can talk about it. Yeah.
So,
Was that Rafi who posed this question?
Yes,
Was it
like,
Rafi? Yes. So let's talk about it afterwards, okay?
yeah, maybe we should not, we are already over time, so maybe we allow him to finish and wrap up his talk.
Yeah, so okay, so if there are no questions, this is the story for bosonic fields, and okay, and the fermionic fields. Okay, so the fermionic fields is a little different. Okay, so let me show you what. Well, spin half, you know the story. So let me tell you what. Anyways, by the sketch. So these are the projectors mapping you to the positive and negative Helicity modes, and they satisfy the Dirac equation. Okay, so you can write down their similar Lagrangian description. You can write down for each mode Dirac Lagrangian. Okay. The similar thing, the story for same for the psi minus. And okay, so here because it's a first order time derivative. Okay, it's a first order time derivative. Okay, here we cannot just go ahead and take so because if you break it down, you have this thing. Okay, if you use the matrix and you have these terms and you have a di here, it's 1 over c here. Okay, and the thing that we did for scalars, we cannot do it that way. Okay, so what we did for scalars. Okay, so we had this thing, we identified the so okay, so here you already have this independent UF, so you don't have phi naught issue. Okay, but when you throw away the phi naught, you end up with this equation. So this is the Klein-Gordon equation, which has 1 over c squared there, and you can actually control 1 over c squared behavior by plugging in this thing. Okay, and you can drop off. So you can say, take say goes to infinity, these things drop off, and you find the first order time derivative by this mechanism. But here you are already first order in time to begin with, so there is nothing else to do. This mechanism is not necessary or needed for Dirac formula. It's already first order in time derivative. Okay. So what you do instead, that you take the Dirac Lagrangian, okay, and it is C inverse L. You don't take non-relativistic limit here, but it you take this Lagrangian, you get the equation of motion from here, okay, which is the Dirac equation of motion for each of them. Okay, so you can combine them. Actually, psi plus and psi minus, you can combine them and you call this a psi, okay, which has 2 DOFs. Okay, equal to m psi. So you have a Dirac equation, and from there you work through. Okay. So here you can write down the Lagrangian for the independent modes, but you cannot do the, you cannot come to this level because it is already in this, at this level for the Dirac, Dirac or fermionic case. It is already in 1 over time, and it already has a 1 over c that you cannot just drop by anything you try. It is 1 over c there, so you cannot drop it. So what you do is you take the Lagrange equation of this Lagrangian, and then find the Dirac equation. From the Dirac equation, you go to Klein-Gordon for this psi, and then do the same business as we did earlier. Okay. So that's the story for spin half. The same story one can do for spin 3 half. Okay. The spin half already had the right degrees of freedom, but spin 3 half is not. It has gauge symmetry as we saw. So again, you have to do the projector. So this is the last bit, and by saying this, I will end the discussion. And of course, take questions. So if you apply the projector, you end up getting this expression. Okay, again, I'm suppressing. So my A's are vector indices. I'm suppressing all the Dirac indices. Okay. Gamma A. Okay. It shouldn't be gamma A because gamma A should not be contracted. B, C's are contracted. So yeah, okay, this is correct. So okay, good. So this is the projector. Again, we have one of our box sitting outside. Okay, good. So okay, so from okay, good. So from here one can prove. So what? Okay, so what is this psi that I was talking about? This psi, to begin with, we have to consider a psi which is gamma traceless. Okay, to begin with, this is gamma traceless. You start with a theory which is a gamma traceless spin 3/2 field. Okay, so you have to have this constant to begin with. Okay. Then you prove from this by inspection. This obviously satisfies gamma tracelessness. Okay, you can just see this, and because this term is already 0, and if you take gamma here, this, okay, this term will drop off, this term will drop off, because again, because gamma traceless is 0. So this term, obviously this expression satisfies this gamma tracelessness condition that you begin with. So the projector respects that. And also, because the projector is a transverse projector, it must satisfy the transversality condition. Okay, that you can verify just by applying dA. So the dA part is easy to show, because dA part, this term would be 0 because it is antisymmetric, and these two terms will cancel each other. dA square would cancel the box again with the subtlety, and d dot psi and this psi will cancel each other. So you have your constraints again. This is equation 1, equation 2. So how many constraints? This gives you 1 constraint. This gives you 3 constraints, because I'm in 3 dimensions. So therefore, you have in total 4 constraints. Okay. And if you do the counting of DOF, so how many degrees of freedom do I have? So I have, it is in 3 dimensions, I have 3 times 1 complex DOF. Okay. I have 3 real DOF, and I have 1 complex. Okay, so for spin 3/2 field in so it's a Dirac spinor, which has positive and negative helicity modes, right? That's the idea. So it has, so you have 6 DOF in total. Okay, so you subtract out 4 DOF, so you end up with 2 DOF. Now these are real DOF. So ultimately you end up with a proper counting of 2 DOF, and then that should be the case. DOF do not change if you consider equation of motion approach or Lagrangian density approach. Any question? So one goes through the calculations of Schroedinger Lagrangian or spin 3/2 Lagrangian that we saw momentarily before, probably half an hour before. And you plug in some identities here. I don't think I have. I want to show you these things. You can check out these calculations. This will be just. If you want me to show you, I will. But I don't think anybody wants to do this right now because it's too late. So you do the calculations. You plug in these expressions, and you really, and also these constraints. Also importantly, these constraints. Okay. So you end up getting nothing but the Dirac Lagrangian as the dynamical Lagrangian, and then the story goes similar to spin 1/2. Okay, once you have this, then you can just take it from there. So that's the idea for other arbitrary other fermionic fields.
Okay, so is that what you want to talk about?
Yeah.
Okay, so we thank the speaker for the nice talk. And yes, in case any of you have question, I think most of the audience are already left. But anyway, we are here. If any of you have question, please feel free.
I think we asked all the questions there was to ask.
Yes, we talked a lot. So we thanked Abhijeet, at least virtually or by a physical clap.
Sorry for being late.
Thank you, everyone. And today was our last talk for this session. The next session will start on February. You all are cordially invited. Okay, most of the people anyway know, but I will keep you emails updated before the next session.
Thank you very
Thank
much
you
for giving me
very much.